So what are the electron donating groups? Remember, electron donating groups are R groups that are going to stabilize intermediates on our way to the ortho and meta product. So I'm going to redraw one of our previous resonance forms. We call this resonance form number 8 in an earlier video. And so we need to think of R groups that are going to stabilize this carbocation right here. So we need R as an electron donating group to stabilize that carbocation. Well, what sort of groups stabilize carbocations? The fact is, alkyl groups, they stabilize carbocations. They stabilize them by hyperconjugation. Conjugation, can I spell it? Conjugation, yes. So they stabilize by hyperconjugation. Therefore, if we have alkyl groups on the ring, they are ortho-para-directors and activators. They make the reaction go fast. Activators. What other groups can stabilize a carbocation? Well, as it turns out, oxygen atoms, like ethers like OCH3, even things like esters. It's a little ugly, but it's all about that lone pair. So ethers and esters. So what does this look like? Let's go over here to the right. Let's put a methoxy group on that carbon. It turns out that lone pair on that oxygen can donate in, and you go from a non-octet satisfied carbocation to an octet satisfied oxonium ion. And you might say, hey, but look, you put the positive charge on oxygen. That's terrible. You're right. However, the number one rule in Lewis dot structures is to satisfy octets. And this structure, the lower resonance form, is the better resonance form because it has a full octet. So that oxygen, through resonance, can help stabilize that lone pair. Stabilize a carbocation. So nitrogens can also, in many cases, stabilize that carbocation. And I'm talking specifically about amides. Now, if we put this group, this amide group, in place of our OCH3, we could use this nitrogen lone pair in exactly the same way and draw an extra resonance form and stabilize a carbocation. Great. Amides are therefore ortho-para-directors and activators. However, I am not talking about amines. Amines are not activators. So what's the problem with amines? Well, in almost every electrophilic aromatic substitution, what happens is, and let's put an amine on here, try to make it legible. We do an electrophilic aromatic substitution, and if you go back and look, almost all these are performed under acidic conditions. Well, what is this amine going to do under acidic conditions? It's going to get protonated. And once you protonate that nitrogen, this is no longer a potential activating ring. In fact, it's a strong deactivator. So, in theory, even though amines should be good activators and ortho-para-directors, the fact is they get protonated and they're terrible. And it's just an artifact of the fact that we're under acidic conditions. Other nitrogens, oxygens, alkyl groups, those are all great ortho-para-directors and activators for electrophilic aromatic substitutions.